We are going to continue with the homework now with number 26. And number 26 states that certain nucleides listed are not in the band of stability, and it asks you to predict what sort of decay would occur. And I'll try to help you understand this as we go through. The first one is phosphorus 3415. Now, as we look at that, normal phosphorus is 3015. And so what we have here is too many neutrons. And as it turns out, if you have too many neutrons or a high neutron to proton ratio, what occurs is an attempt to get rid of neutrons. And the way the neutrons are most commonly gotten rid of is the production of a beta particle. Now, why is that? Well, what happens is a neutron is changed into a proton plus an electron, and this electron represents the beta particle. So with this one, the most likely decay is to do beta emission in order to get rid of some of those neutrons. The second one, uranium-239-92. Now, as it turns out, with very large molecules that have a large atomic weight, in order to get back to the band of stability, frequently the first step is to emit an alpha particle. And the alpha particle is a helium nucleus. And the reason for that is that this is the fastest way for these numbers to get to where you want to go. We can look here at this, for example. This is the answer sheet for this problem. And what you see is it says atomic number greater than 82 alpha decay. When you have a high atomic number, then you end up with an alpha decay. Another thing, and so that's number 2. Number 3 is 3720 calcium. Now this one has exactly the opposite problem that this one is. You know that calcium is normally, in normal situations, 40-20. Okay, and that's, so you have, instead of too many, you have too few. And as it turns out, when you have too few, what you go for is what's called a positron emission. A positron is an electron with no weight and a positive charge. Now, the reason for that is that tends to, let me read it here for you. Positron emission is observed for nuclides in which the NP ratio is low. These nuclides below the band of stability are below the band of stability. Positron decay is the conversion of a proton into a neutron to produce the positron. So what happens is the proton is changed into a neutron plus the positron. And so because in this case you need more neutrons, you want to convert to bring this ratio together. This was the high NP ratio. This is when you have a low NP ratio. A low NP ratio. So let's look at D. 9,3 lithium. Now, lithium, I can tell right away that this has a very high NP ratio. There's lots of extra neutrons here. So beta decay is certainly going to be one of the things that we will see. And then lastly, 24596. Again, this is the same as this up here, so you're going to primarily see an alpha decay. So that's number 26. The next problem is number 30. And number 30 states the following. write the nuclear reaction for each step in the formation of lead 20882 from thorium 22890, which proceeds by a series of decay reactions in a stepwise manner. And then it gives you the steps. And so in the order. So we're going to go through that. We start out with 238, 90, thorium. And it states that you emit 4 alpha particles, then 2 beta particles, then an alpha particle. So you have 4 alpha particles, 2 beta particles, then an alpha particle. So let's see what will happen with each of these. So first of all, you go from thorium, and you're going to give up an alpha particle. And so that's going to reduce this to 234 and this to 88. And if we look in the periodic table, what is the atomic number of 88? We find radium. And so radium is the first product. So that's the first alpha particle. Then we have 234, 88, radium, and it breaks down, and it's going to go to 230, 86, whatever that is. And that, if we look at that, that's going to be radon, Rn, plus 4, 2. So that's the second alpha particle. The third alpha particle is going to take radon, and it's going to go to 226, 84. And 84 is polonium, PO, plus the alpha particle. And then the last alpha decay is going to go from 226, 84, polonium, and you're going to end up with 222, 82, and that is lead. So that's your third or fourth alpha decay. Now, you're not to the point that they've asked you for, but you're at lead. So you have 222, 82, lead, and then it says there's a beta decay. Well, a beta decay means that you end up with 83, 222, because a beta particle is a -1, remember that. And 83 is now going to be bismuth. And then you do bismuth, 222, 83, and another beta particle. You end up with 222, 84, which is polonium again. So that's the second. And then the last step, I believe this is, yeah, the last step is to take bismuth, 222, 80, or polonium, 222, 84, and do an alpha decay, which will take 4 off the top, 218, and 2 off the bottom, 82, and you're back to lead plus an alpha particle, which is a 4, 2 helium. And so let's see if that's where we want to be. So we had 4 alphas, 2 betas, and alpha in that order. So we don't end up at 208. So I'm not, this is, unless I made a math mistake in here somewhere, it's 218, not 208. So I'm not sure what happened there, but there's an alpha there, an alpha there. Do we start with 238 or 228? Maybe I got that wrong. Yeah, it's 228. That's where I made the mistake. So this is 228, 224, 220, 216, okay? And we end up with this alpha, this one's going to be 212. So this is 212, and this is 212, and then you end up with 208 here, 212. Sorry about that. I wrote this down wrong. This should have been, so all this is correct except I just miscopied this one. So you go from 228 to 224 to 220 to 216, and then you end up at 212. Then with 2 beta particles, you just step back up. Then you end up here, and then with the last alpha decay, you end up where you're supposed to be. So that's number 30. Now the last homework problem is number 34. And number 34 states that the isotope of thallium, 208, undergoes beta decay with a half-life equals to 3.1 minutes. Okay, if we look at the periodic table, we find that it has a atomic number of 81. So the first question is, what's this beta decay look like? So 208 thallium, 81, goes to form 208, 82, plus a beta particle. And let's see what that is. 82 is lead. So it forms lead when it breaks down. So that's answer to A, which it says what is the isotope produced by the decay? The isotope produced by the decay is lead 208. B. How long does it take for 99% of the sample of pure thallium to decay? Now, in order to do this, you need to look at page 1091. Now, one thing we didn't do this year, which I've done in years past, is the chapter on chemical rates. And I skipped that chapter because it's conceptually quite hard for students to pick up. But there's a couple of equations here you need to use and have in your hand in order to do these calculations. And I would strongly recommend, for the purposes of a quiz or test, that you understand these two equations. The first one is, both of these are on page 1091. The first one says that the half-life is equal to 0.693 divided by something called gamma, which is the kinetic constant, or the decay constant. The second equation that you need, that we'll get to in just a second, is also right on that page. And what it shows is that the amount of sample after a certain period of time is equal to the original amount of sample times E raised to the power of minus KT, where K represents the elimination constant and T represents the time that it's passed. Now this can be solved for a separate, where T, you solving for T, you get 1 over, actually this is better to call it lambda than K, 1 over lambda natural log is the inverse of the E when you raise something to the E power, of the amount of sample after the time has passed over the amount of sample you started with. And so this, if this is the equation you need if someone tells you a certain amount of time has passed and they want to know how much sample is left. They tell you the original amount of sample and they want to know how much sample is left. And this is what you need if you have to calculate a half-life. Or if they give you the half-life, you can calculate the decay constant. And so in this problem, what they've done is given you the half-life. And so we can calculate the decay constant, because if we rearrange this equation, the decay constant is equal to 0.693 divided by the half-life. And in this case, the half-life is, it's going to be 0.693 divided by 3.1 minutes. And so that's going to equal 0.224 minute minus 1. The decay constant is in an inverse or per minute, in this case per minute. And your answers are going to be in a minute, in minutes. So going back to the actual question, I just did that as sort of introduction. The question B says, how long will it take for 99% of the sample to decay? Well, what this tells you is that N0 is 100% and NT is 1%. That's what's left. Okay, so you have T is equal to 1 over gamma log NT over N0, and NT over N0 is going to be 1 over 100. So it's the natural log of 1 over 100. So you have T is equal to 1 over 0.224 times the natural log of 0.01. And if you get your calculator out, that's actually not hard to find. So 1 over 100 is 0.01, and you can see it there on my calculator. It says log to the base E, okay? And on some calculators it says ln, okay, which is the same thing. And I forgot the minus sign here, I'm sorry to say. This is a minus sign. So, and the natural log of this, so we have minus here, natural log of this is minus 4.61. So now if we take that and do the math here, T is going to equal 20.6 minutes. So the amount of time it takes for 99% of the sample to go away is 20.6 minutes. Now if you think about it, 1 half-life it goes to 50%, 2 half-lives it goes to 25%, 3 half-lives it goes to 12.5%, 4 half-lives it goes to 6.25%, 5 half-lives it goes to 3.125%. So, you know, at 5 half-lives, so 5 times that number, you're getting pretty close to 1%. So you can see that this, just in your head, you can see that this is pretty close. And then it says how much or what percentage of the sample of pure thallium will remain undecayed after 1 hour. Okay, now what we're doing is solving for this instead of solving for T. And there's a couple ways you can do that. It says what percentage, so you can write this original equation like this, and you can say that you start with 100, e to the minus, and then put 0.22, what was it, 0.224 times t, which is 60 minutes, and then do the work here. Let's see what that comes out to. We have, let's start out with 60 times 0.224. Now on your calculator, if you look, there should be an e to the x. And x here is 13.44, that multiplication you just did. So if you do that, okay, if you do the math here, if you multiply these two together, you get a minus 13 and change. If you raise e to that power, you get a very small number, and then multiply that by 100. You end up with 1.4 times 10 to the minus 4. And that would be percent. Because you started out with 100, that's 100%. So this is how much would be left after 1 hour.